All right, so we'll connect an AC source to a general circuit, and we will be interested in the amplitude of the current and the phase shift phi. Of course, we won't do anything like complicated like this in this class. What we'll do is we'll start off by just connecting a resistor and then just connecting an inductor, just a capacitor, and then the last thing we'll do is connect the three in series. All right, so here's an AC source connected to a resistor. Okay. So the voltage across the voltage being supplied to the resistor is V max sine omega t. Okay. And the current is V max over R sine omega t. Okay. And you can see from this expression, if you compare it to this general expression, phi is 0 when this is a pure resistor. This is phi is 0 and Z is equal to R. Okay. So as expected, Z equal to R and phi is 0. Okay. So nothing much interesting is going on with the resistor connected to the thing. So here's the AC source, here's a resistor, and we'll start it. So the AC source gives you an AC current. So the brown curve is the voltage and the purple curve is the current. Okay. And you see the current keeps in lockstep with the voltage. And as the voltage rises, the current rises in the resistor. What you'll see is you will find that this is not true when you connect a capacitor or a inductor. Okay. So only a resistor the current keeps in lockstep with the voltage. Okay. Now let's look at this guy. This guy is called a phasor diagram. Okay, and this guy is useful. And we'll get to that in a minute, but I just want you to notice this. So, okay, so the phasor is two vectors, and the magnitude of the vectors are equal to the amplitude of the voltage and the current. And these vectors are rotating at the angular speed of omega t. Okay, so they're rotating at an angular speed of omega. So the angular velocity, the angle to which they have rotated is omega t. Okay, we'll come to that in a second. So let's look at the voltage. Okay. All right, let's first actually go to the chalkboard. Okay. So what the phasor diagram does is the following. Okay, so now let's do vectors first. Okay, you guys remember a vector A. Let's say this is the angle phi, and A is A cosine phi I plus A sine phi j. Okay, so the y component of the vector is given by A sine phi. Okay. So if you look at this, the voltage, the AC voltage, V sine phi, sine of this angle. So you see the instantaneous voltage being supplied to this resistance is like the y component of this vector. And that's what that phasor diagram is. Okay. So the instantaneous voltage is the y component of this vector, and the instantaneous current across the resistor is the y component of this vector. And that is what's being plotted here. This is the y component of these vectors. And these vectors are rotating at an angular speed of omega. Okay. So, and this will be very useful later. Okay, it'll help you. I mean, this phasor will help you. Otherwise, there might be solutions to problems where you might have to solve differential equations, but using these phasors, you can avoid that. Okay, so these phasor vectors rotate at an angular speed of omega, and their y components give you the instantaneous value of the current and the voltage across your circuit. Okay. So right now this is fairly simple. Okay. All right. So now let's. So an AC source connected across the resistor. You see that. So this curve is the voltage, and this curve is the current, and you see the current keeps in lockstep with the voltage. All right, so you saw phasor diagrams can be useful. There are the phasors, and the brown phasor is for the voltage, and the purple is for the current, and there's the voltage, and there's the current. Okay. All right, now what we'll do is we'll define something called that RMS quantity. Okay, so in this circuit, we have connected an AC source to a resistor, and the power delivered to the resistor, meaning if this was a toaster or something, how hot is this toaster burning is related to the power delivered. Okay, so the power delivered is the instantaneous current squared times R, and here is the current, and here's R. Okay, so the current varies sinusoidally, and if you take the square of that, there's the current. Okay, in the US, that's one cycle. So in the US, the AC source has 60 cycles per second. Okay, so if you come here, that means these peaks, you have 120 peaks per second. Okay, so the power peaks like that 120 times a second. So in fact, if you have a bulb, like let's say an incandescent bulb, the bulb brightens 120 times a second. It brightens and goes dim 120 times a second. But that's happening so fast that your eyes can't tell the difference. Okay, so if anything flickers more than 30 times a second, to you it's a continuous motion, and that's how movies work. For instance, if in a movie theater, they project one frame at a time. But if the frames are projected faster than 30 frames a second, then the motion will appear continuous to you guys. All right, so that's what's happening. All right, anyway, so bulb will flicker 120 times a second. Okay, so of course, you're not interested in these detailed time information. Now, all you care about is the average power. Okay, so you take this expression and you average it over one cycle. And if you average sine squared theta over one period, what you find is the average is 1/2. Okay, and you can do the integral. So it's 1/2. Okay, so here is the power delivered to that resistor. Okay. Now it's I max square R divided by 2. So let's go to the whiteboard. There you go. All right, so the chalkboard, let's say, okay. So here's a DC circuit. Okay, voltage, current, IR. So the power delivered to the resistor is I square R. Okay, now we connected an AC source to the resistor, and what we found is the power delivered is I max square divided by 2 times R. Okay, so this factor of 2 is annoying. We would like an expression, something like, for the AC source, we want an expression that looks like this. So what we'll do is we'll define something called IRMS squared times R. Okay, so what we're defining is, now I'll come over here, IRMS squared equal to I max squared divided by 2. Okay, so we define this new quantity IRMS. It's called the root mean squared, and that's what it stands for. Okay, so and the only reason we define that is so that we have an expression that looks like the expression for the DC circuit. Okay. All right, so when you take the time average, you get I max over 2, and this, because this factor is annoying, we've defined something called IRMS current, the root mean square current. And here's how it's read, and here's where the name comes from. Okay, this is the square, there's the square term, and you take the average over a cycle, and that bar is for the average, and the average gives you 2. Okay, and then we want to name, so if you take I max divided by square root of 2, we'll define that IRMS. So that's where the root comes from. Okay. Anyway, so IRMS is root mean square. Okay. And that turns out to be I max by root 2. Okay, again, the whole spiel is just so you have an expression for the power delivered very similar to, so you want this expression to look exactly like that for the DC circuit. Okay, so that's how come we define IRMS values. Okay, and so in these AC circuit problems, you can so that's a generalization for sinusoidal voltages and currents. VRMS is also equal to Vmax by 2 root 2. IRMS equal to Imax by root 2. And if you have any DC expression, so for instance, for a DC circuit, the power delivered to the circuit is V times I square R, and V square over R. Okay. And so if you go to an AC circuit, the expressions can be generalized as long as you replace each of these values by RMS values. RMS times IRMS. IRMS squared times that VRMS squared divided by R. Okay. So that's a good thing to remember about the RMS values, root mean square values. You can substitute in any expression for in DC circuit, you can substitute these values. Okay. Oh, actually, we'll have to correct this. We'll come to that in a second. For a purely resistive circuit, this is true. Okay. So we'll come to that in a second. All right. All right, so that's what our RMS values are. Okay, now what we'll do is we'll connect an inductor. Okay, so we're keeping things simple. We started off by connecting just a pure resistor. Now we'll connect a pure inductor. Okay, so we have our AC source, and we want to see how this inductor behaves when you connect it to a AC source. Okay. Now here is a complete loop, and Kirchhoff's rule, Kirchhoff's law, one of Kirchhoff's law says the sum of the voltages across all elements in this loop add up to 0. So the voltage across this element is V max sine omega t. The voltage across the inductor is minus L di by dt. Okay, so here is this differential equation that you get. So this differential equation describes the behavior of this circuit. And you got this differential equation from Kirchhoff's laws. And you can solve this differential equation. Okay, so V is Vmax times Vmax sine omega t. And if you solve this differential equation, what you get is the current is Vmax omega L sine omega t minus pi by 2. Okay. All right, so remember, let's go back to our circuit. Okay, so what we were interested in, you have an AC source, you connected your circuit to the AC source. The AC voltage was V naught sine omega t. The current through the circuit, so the current, okay. So this is, oops. This, wow. This is kind of annoying. All right, so there's the voltage and there's the current, and the current is the amplitude of the voltage divided by the impedance of this circuit, okay? And phi is the phase shift. All right, so let's look at the expression for the inductor. So with the inductor connected, you see, so that is the impedance of the inductor. That is the resistance of the inductor. And you see that's frequency dependent. And the phase shift is pi by 2, which is 90 degrees, okay? So the current lags the voltage by 90 degrees, okay? So that is what the solution of the differential equation is telling us. So it's given us the impedance of the inductor and the phase shift that we were interested in. So this is given us a special name. It's called, the impedance is for the inductance, this is called the inductive reactance. It's denoted by XL, that's the standard notation. And you see it's frequency dependent. So that's the resistance of the inductor. And you see as the frequency increases, the inductive resistance increases linearly, okay? Current lags voltage by 90 degrees, and inductive reactance is this, okay? So let's look at the simulation for that. All right, so here's the AC source, and here's the inductor, and here is the current phasor, here's the voltage phasor, and you see the current phasor lags is 90 degrees behind the voltage phasor, okay? So if you start, it's always 90 degrees behind. And you see, so here's an interesting thing. The current is 90 degrees behind the voltage and it's not in lockstep. So there are times when the voltage is decreasing and the current is still increasing, okay? And so there's a phase shift of 90 degrees between the two, okay? Only in a resistor will the current and voltage keep in phase. All right, so that is the inductor. And now we'll connect the last element, the capacitor, to an AC source. Okay, so there is the AC voltage. The charge on the capacitor is the instantaneous voltage times the capacitance, so it's C times that. And the current in the circuit is dq by dt, okay? So the current in the circuit is the rate at which the capacitor is being charged. And you can take the time derivative of that, you get a cosine function, and then you can write it in terms of a sine function, like so. All right, so now let's look at this expression. Let's go to the whiteboard. All right, so. So when we connected an AC source to a capacitor, what we found was the current was omega C V max V naught sine omega t minus phi. Okay, So here was the general expression for the current. Okay. All right, so we are going to write this in that form. All right, so this fella is Z, and that's phi. Let me fix that. And that is pi by 2, pi by 2. Okay, so from this expression, you can see that Z is 1 over omega C. Okay, and this is called XC, and phi is minus pi by 2. Okay, so those were the two things we were interested in. And for the capacitor, Z is 1 over omega C. Okay, so the capacitive reactance is given by 1 over omega C. And you see as the frequency increases, the resistance of the capacitor goes down, okay, it decreases. So that's the capacitive reactance. And phi was minus pi by 2. So current leads voltage across a capacitor, and capacitor reactance is that. So let's look at that simulation. So here was the inductor. Here's the oops. All right, I guess I didn't. Let's show you the capacitor. Okay, so the current is ahead of the voltage phasor by 90 degrees. Okay, and let's start. Okay, so again, you can see that the current and voltage are not in phase, and again, these are y components of these phase vectors, which are rotating at an angular speed of omega. Okay. All right, so the current leads, so the voltage is behind by 90 degrees. Okay. All right, so now we have covered all three elements individually. Now this is the most complicated thing we'll do. We'll connect them in series and analyze that circuit. But before I do that, let me pause and I will let you guys ask questions if you have any.